Hello everyone and welcome to Sky Scholar. Today I wish to revisit our analysis of the second solar spectrum. I have decided to change my approach slightly, providing greater guidance as the conclusions are outlined. In any event, a few days ago this video was released on the subject, and if you have not seen it, you need to do so first. That will facilitate your understanding of this presentation. At the same time, I recognize that the first video on the second solar spectrum moved rather quickly. As such, I wanted to take the time to recap some of the most important lessons. One of the first points I made in that video was that the photosphere itself should be treated as a real black body surface unable to emit polarized light. That is because the light emitted by a black body is never polarized. The polarization we observe in the continuum spectrum, especially as we move towards the limb of the sun, must therefore be created when the photospheric light interacts with material above this surface. Recall that when we refer to the continuum, we are actually referring to this spectrum of the sun. It is that spectrum which becomes more polarized as we look towards the limb. Since the visible light which makes up the continuum is being produced by a black body, it should not be considered polarized as it leaves the surface of the sun. As a result, linear polarization of the continuum must be produced by molecules and anisotropic particles in the solar atmosphere above the surface. The idea that a gaseous sun can produce both a blackbody spectrum for the continuum and then polarize it is simply not reasonable, as I also highlighted in the first video. Astronomers cannot simultaneously argue that a gaseous sun can produce a blackbody spectrum and that such a spectrum gets polarized at the limb, because they have no phase transition which can separate the two effects. They are solely in a gas and their surface is just an optical illusion. It is not reasonable for them to claim that the continuous light of the sun is unpolarized when they want a blackbody, and then the light is polarized when they need to explain the origin of the second solar spectrum. Secondly, I noted that chemical selection of elements has taken place in the sun. This is true not only in the Fraunhofer spectrum itself, but in the second solar spectrum as well. In particular, titanium lines are greatly amplified in the second solar spectrum. I also highlighted the presence of at least 15 two-electron transitions in titanium. These were seen both in the sun and in the laboratory, where experiments were performed in air. Now, these two-electron transitions are key because it is extremely improbable for such transitions to take place. Something must be dramatically altering the probability for absorbing the photons required. The fact that the transition probability for simultaneously absorbing two photons greatly increases is a sign of chemistry. Now consider this schematic to help visualize what has taken place. The titanium is experiencing very weak interactions with other ions, atoms, or molecules in the air when studied in the laboratory. In air, for instance, titanium is able to form weak interactions with other titanium atoms or with nitrogen or oxygen. The distance to these atoms from one another would be greater than if a covalent bond existed. Only weak long-range interactions are required, perhaps on the order of van der Waals forces, which would result in a bond length of 4 to 5 angstroms. So once again, two-electron transitions are extremely improbable. However, transition probabilities can be increased if the ion or atom of interest is somehow being coordinated with other species, and that requires adequate densities. Remember that when I speak of coordination, I'm envisioning a scenario where no covalent bonds are being formed. Rather, the atoms or ions have very weak interactions with their neighbors. In order to confirm that the two-electron reactions represented a chemical effect, I also emphasized in the last video that no two-electron reactions were observed in the laboratory for the unreactive noble gases, namely helium, neon, argon, and krypton. Some two-electron transitions, however, were observed in xenon, but xenon dimers are known to exist. In conjunction, these results are a sure sign that chemistry is at hand relative to the two-electron transitions, both in the laboratory and on the sun. This point is important as it highlights that elevated densities must exist in the chromosphere of the sun. This represents a major blow to the standard solar model, which tells us that this region of the sun is a terrific vacuum. The two-electron transitions also highlight the importance of laboratory conditions when spectra are obtained. This has been known for a long time. In 1895, Ames commented on the importance of laboratory conditions used by Eder and Vallenta as follows. Then, by a most ingenious arrangement, sparks were passed between carbon electrodes, dry or wet, in atmospheres of hydrogen, carbon dioxide, and air. When the spark is passed between the two poles in hydrogen, the smallest number of lines appear in the spectrum, because in other atmospheres like carbon dioxide or air, the gas is dissociated and various other spectra appear. This fact is of interest as indicating the best method of getting spark spectra of other substances such as sodium. The carbon poles can be moistened in a solution of common salt and then placed in an atmosphere of oxygen. How ironic that this appeared in the very first issue of the Astrophysical Journal. Unfortunately, no one really paid attention for nearly 130 years. Yet the author was telling us that far fewer lines were being produced when doing the experiment in hydrogen versus air. Also note how this discussion relates to data obtained under the spark, not the arc. That is important because astronomers also knew that more intense lines could be found when spectra are produced by using the spark rather than an arc, as Saha himself recognized long ago in his classic paper of 1920. Here is what he said. According to Lockyer, the passage from the arc to the spark means a great, though localized, increase in temperature, to which mainly the enhancement of lines was to be ascribed. Saha disagreed with Lockyer that temperature alone was responsible. He then quickly advanced the solution. A much more plausible explanation is that the lines in question are not due to radiations from normal atoms of the element, but from an ionized atom, that is, one which has lost an electron. Of course, Saha was right. It was the ion that was responsible for the greater enhancement of lines when the experiment was performed with a spark. Spark data best represented what was taking place in the chromosphere. Spectra obtained with the spark resulted in the formation of more ions. That logic was correct, but only in part because it ignored the potential for line enhancements by interatomic interactions with the surrounding air. Now let us consider what happened after Eder and Vallenta discovered that the environment surrounding the atom mattered even under spark. Of course, Ames in 1895 could only postulate that the gaseous molecules surrounding the atom of interest were being dissociated into their component atoms. Surely this was happening to some extent, and that would result in additional lines. But what Ames could not have anticipated in 1895 was that weak interactions were also taking place between the ion of interest and other atoms, ions, or molecules in the environment. In order to better understand the problem, let us examine this paper by J. A. Anderson, published in 1924. This time the concern is with the spectrum of calcium using a spark and under vacuum conditions. The paper is particularly interesting because it compares results with those obtained by Eder and Vallenta, as we just discussed. Anderson reports more lines than Eder and Vallenta, and this is seen by examining his Table 1. In fact, if you want to take the time, compare the lines obtained by Anderson in vacuum with those obtained by the NIST. You will be shocked by the number of lines which simply do not agree. The issue relates to whether or not lines from gases in the bulb alter the results, even though the experiment is supposed to be done under vacuum. Here is the key quote from Anderson's paper. The comparison reveals surprisingly few lines which can be attributed to residual gas, which led the writer to believe that the spectra are almost free from lines from this source. A careful comparison of the spectra of calcium, cadmium, and carbon showed fewer than 20 lines which agreed closely enough in wavelength, intensity, and character to be regarded as identical, and all these lines are weak. The author then decides to examine different pressures in the experiment using various metallic terminals. He then notes, and it has brought out very clearly the fact that the air spectrum is different with different electrodes. To give a few illustrations, the great nitrogen pair at lambda 4097 and lambda 4103 is present with calcium, absent in cadmium, and extremely weak, if present at all, with carbon. The enhanced oxygen lines at lambda 3754 and lambda 3760 are fairly conspicuous with aluminum, weak with calcium and carbon, and extremely weak, if present, with cadmium. So now we see that the nitrogen lines are present with calcium even under low pressure, but they are absent when cadmium is used. This is telling us one of two things. Either calcium is enhancing the nitrogen lines, or that cadmium was interacting with nitrogen and shifting those lines to other wavelengths. This directly points to chemistry, an interaction between cadmium and nitrogen under these conditions, which causes the nitrogen lines to vanish. Surely, after all, nitrogen was still present. Now here is another great quote from that paper. With the metals calcium, zinc, cadmium, and aluminum, it was found that when the electrodes became hot and sparks were passed at a rate of 1 every 5 seconds, the pressure would fall so low that the gap became non-conducting. A wait of a few seconds would, in such case, allow sufficient gas to diffuse back from the pump to permit discharge to pass again. Such an effect was expected with calcium, since it is well known that the hot metal will absorb all common gases, but its occurrence with other metals was a little surprising. It did not occur with magnesium, iron, copper, or lead. What are we being told here? Namely, that calcium was reacting with common air when the sparks occurred, and this caused the pressure to drop. The ion was thereby removed from the gap region and the spark could no longer occur. It is well known that reactions can alter the partial pressure of reactants in a gas as products are formed and the pressure subsequently drops. Anderson's paper is filled with warnings about chemistry, but the astrophysicists simply chose to ignore the findings even though the results were published in their own journal. Finally, we come to this great classic by Olmsted, published in 1908. In this paper, Olmsted produces calcium hydride in his experiment, and he uses the resulting spectra to assign calcium hydride lines for the first time in sunspots. The trick in this case was to allow calcium-based electrodes to interact with a hydrogen atmosphere. Here is the relevant quotation. The bands appear when an arc formed between metallic calcium electrodes burns either in commercial hydrogen or in hydrogen formed from zinc and hydrochloric acid and dried with sulfuric acid, but do not seem to appear when the same electrodes form arc in air. Also, these bands do not appear when dry calcium carbide is used as electrodes in air, but do appear if wet cotton surrounds the electrodes. The bands appear when calcium metal electrodes are burned in air if a stream of steam or hydrogen enters the arc through a hole bored in one electrode. For those who have not read Olmsted's paper, it is particularly worth a look. It is only 3 pages long and linked below. It is a real classic in astrophysics. In any case, the point is that when we study spectra in the laboratory, the conditions present dramatically alter the findings. There is a difference between air and hydrogen. With calcium, when a hydrogen atmosphere was used or when steam or water was present, a molecule of calcium hydride was produced. Now, in air, nothing prevents calcium from having weak interactions with oxygen or water, for instance, as calcium is known to quickly react with either. Short of such reactions, nothing is preventing a calcium ion or atom from having weak interactions with oxygen or water in air, short of forming an actual molecule. And that is the point. An atom or ion studied in air can interact with other species in that environment in a manner which is completely unsuspected when the NIST tables were prepared. So how is the problem of differing environments solved? For astrophysics, the decision was made that the experiments should be done in air in the visible range, and that is what the NIST does to this day. Now think about this for a moment. Why air? Why not vacuum? Obviously, when the experiment is done in air, there will be a lot more transitions. Some of these can be easily assigned to atoms and molecules making up the air, and those will be a constant contamination to the line spectra. So why not get rid of the air and collect the spectrum in the cleanest possible way? Why not just use vacuum? The answer is easy. Some atomic lines were being enhanced by the use of air. If one does the experiment in vacuum, those lines might be gone or might be much weaker. So for the astronomers to be able to identify all the lines on the sun, they need as many lines as possible in the laboratory, and that only happens in air. However, when the studies are performed in air, physics is no longer alone in governing what is happening to the atom or ion. Now chemistry is involved, although no one ever considered the complication until now. Even in vacuum, one must be careful not to form dimers, so the situation is actually rather complex to analyze. Weak coordination could be taking place between the atom of interest and other atoms and molecules in the environment. Coordination could act to stabilize metastable states, for instance, or enable transitions to take place which should otherwise be forbidden by the selection rules. In addition, coordination can open the possibility that two electron transitions could take place. So now we have a mess and not the clean line data that the NIST believes it possesses. The problem is that proper studies must involve different environments such that we can gather which lines are affected when conditions are altered. Another problem is that the astronomers believe that the solar body can be treated as an ideal gas, and that the photosphere and the chromosphere are terrific vacuums. They have no room for chemistry. But the line data tells us that something important is occurring in the laboratory. We are getting interactions between ions of interest and its environment, which is altering the transition probabilities. If air was not used, a lot of lines would not be present. Now, a note of caution here. When one examines the NIST table, one is seeing transitions for a particular atom or ion. We know the energy levels of the species involved, and therefore we can be certain that the transition wavelengths are correct. So there is no problem in the NIST tables relative to what wavelengths should exist in a particular spectrum. The tables are extremely valuable in this regard relative to identifying an individual ion or atom on the Sun. The problem rests only in the intensity of the transition and in the value which we should associate with the Einstein coefficients observed in the laboratory. Both of these can be affected by weak transient interactions with other atoms, ions, or molecules in the air. Now, given that air is required, what have we learned? We have learned that chemistry is involved both in the laboratory and on the Sun. This is the first clue that the density of the chromosphere is not near vacuum. The density of the chromosphere is many orders of magnitude higher than currently believed. If the astronomers wish to contest the point, let them ask the NIST to publish line data in vacuum in the visible range for all the important elements. It will be instructive to notice what lines disappear from the NIST tables as transitions are no longer enhanced through coordination effects beyond what would be achieved with dimers. But even in vacuum, one must be careful. Chemistry can still be at play. That is because very dense plasmas are known to form microfields, which may be due to many body interactions with discrete charged particles, as one can learn in this paper. It is reasonable, therefore, to advance that similar interactions take place in all gases when densities are sufficiently elevated. Yet dense plasma microfields are not required to have coordination. An atom could be coordinated in the Sun simply by the interaction with condensed matter. In any event, it is time to bring inorganic chemistry into our interpretation of the NIST tables. Inorganic chemists are best suited to think about what interactions could be taking place between an ion of interest and air. Remember that in the case of titanium, inorganic chemists well understood that the element loves to react with both oxygen and nitrogen, as we saw in the first video. Now, in that video, a great amplification of the rare earth ions was also noted, and these are known to react in the same manner. Again, this is a question of chemistry, not physics. Similar amplification was observed for several molecules, including magnesium hydride, cyanide, and the carbon dimer. Again, these observations point to chemistry taking place in the chromosphere. That is a real problem for the standard model of the Sun, as it advances densities of only 10 to the -7th atoms per centimeter cubed in the photosphere and 10 to the -12 atoms per centimeter cubed in the chromosphere. These values represent powerful vacuums, much stronger than anything ever created on Earth. Yet one cannot have chemical reactions under the conditions advanced in the chromosphere in the standard model of the Sun. It takes density to have chemistry. As a result, the presence of molecules in the chromosphere of the Sun makes it clear that the densities advanced by the standard solar model are simply not reasonable. As a consequence of all this, it was also emphasized in the last video that astronomers have to be careful in applying Einstein coefficients obtained in the laboratory to the Sun. Once again, such coefficients only make sense if one can ensure that the atom or ion is completely free from all interactions with adjacent chemical species or with condensed matter. Now, if you examine the NIST tables, you will see that an Einstein coefficient is often provided for the transition from an upper energy state to a lower energy state. This is the AKI column in the table. The value of this Einstein coefficient is critically dependent on the upper and lower states of the species undergoing investigation being free from all interactions. If the atom or ion is interacting weakly with its neighbors, then the value of this Einstein coefficient will not be the same as for the free ion. For instance, interactions with atoms or molecules in the surrounding air might act to stabilize unfavorable or metastable upper states. That would dramatically alter the Einstein coefficient. This is a significant problem for the astronomers, as they now are uncertain about the true nature of these coefficients in the laboratory. Then we have the sure knowledge, denied by the astronomers, that coordination is taking place on the Sun. As a result, scientists cannot use the NIST values for spectral lines to provide insight relative to the abundances of elements or relative to the density of the chromosphere. This poses a tremendous problem for all of astrophysics, not only relative to the Sun, but also in evaluating relative abundances or densities in any other celestial object. In fact, the problem relative to chemical coordination of ions invalidates thousands of papers in astrophysics. Now, if you do not believe me that coordination takes place in the chromosphere, then just have a look at this image of chromospheric spicules taken in the calcium-2 line by the Japanese Hinode mission. The spicules are just tiny little hair-like projections on the limb of the Sun. One does not see just a random cloud here. The spicules are clearly seen, and it has been known since the days of Angelo Secchi in the 19th century. Next, have a look at this image of spicules taken in hydrogen alpha. Now ask yourself, why are the spicules seen in calcium-2 and hydrogen alpha as we look at these pictures? This is happening because the calcium ion and the hydrogen atom are being preferentially coordinated by these structures. That is why the calcium-2 and hydrogen lines are so broad on the Sun. One is seeing the effect of chemical coordination, not simply temperature or elevation, as the astronomers claim. Again, we are not observing just a cloud of material. We are seeing coordination and structure. The spicules extend from their base at the level of the photosphere to 5,000 kilometers or more in elevation. Along these lines, here is a great quote from Harold Zirin. Years ago, the journals were filled with discussions of the height of the chromosphere. It was clear that the apparent scale height of 1,000 kilometers far exceeded that in hydrostatic equilibrium. In modern times, a convenient solution has been found. Denial. Anyone can measure its height with a ruler and find it extending to 5,000 kilometers. Most publications state that it becomes corona at 2,000 kilometers above the surface. We cannot explain the great height or the erroneous models. While models say 2,000 kilometers, the data say 5,000. In reality, chromospheric spicules are known to extend to heights up to 15,000 kilometers, well into the coronal region. This directly invalidates the idea that coronal temperatures are at millions of degrees, as we saw in this video. That is because spicules are imaged in ions or atoms which are not able to exist at the accepted coronal temperatures. There remains great controversy about the nature of spicules, and you can learn more about spicules in this paper and many others. Spicules are known to be associated with magnetic fields, as one can see in this figure from my own work. In the past, spicules were portrayed as formed between field lines. Now, some are advocating that they are directly associated with the lines. Of course, the chromosphere is filled with magnetic fields, but there are many problems with the direct association of spicules with such fields. This includes the fact that spicule growth can accelerate with increasing height, and that as it grows, a single spicule can expand laterally or split into two or more strands after being ejected, as one can learn in this paper. It is not possible to split a magnetically associated structure into two or more strands, even though theoretical arguments to this effect have been attempted. In the laboratory, physicists have tried to understand the nature of spicules by studying liquids placed above a speaker in audio. Such studies do not involve magnetic fields, yet are also missing the mark, in my opinion. The reason that solar physicists are unable to properly understand spicules is that they refuse to accept that condensed matter exists in the chromosphere of the Sun and that spicules represent condensation processes. Spectroscopic studies of spicules imply coordination of atoms or ions used to generate these images and highlight that there is definitely condensed matter in the chromosphere. So there is no doubt that solar physicists have to be careful in applying Einstein coefficients to atoms or ions found in the sun. Well, that is all for now. I hope that this video helped to clarify many of the concepts presented initially. In the next episode, we will begin our review of the group 2A elements, as they are responsible for many of the most prominent lines both in the Fraunhofer and in the second solar spectrum. We will start with beryllium and ask the question, where are the beryllium lines? I believe that you will be in for a treat. In any event, if you enjoyed the video today, promote the channel, mention the videos to your friends and to your local astronomy club, support me with a like, and subscribe for more videos as we look more closely at the sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on the next video.